Hi guys, today we're going to be going through how to answer rates of change questions when they pop up in the HSC and in trial papers. So rates of change questions usually have to do with some sort of exponential function. Sometimes you'll have to solve with log to find the exponent, and sometimes you do have to work with either the first and second derivative to see how the function is increasing or decreasing, how it's approaching certain limits. So specifically, we're going to be going through question 26 of the Maths CSSA 2024 trial paper. So for this question here, we have an electric vehicle with an empty battery is being recharged. So the capacity C% of the battery while charging at time t minutes can be modeled by this equation. So our exponential equation for this rates of change function is going to be C is equal to 100 outside of 1 minus 2 to the power of negative kt. We're also given a scenario here that the battery is charged to 35% capacity after 50 minutes. And we need to then show that the value of K is equal to 0.01243, correct to 4 significant figures. So in order to find our variable K, which is in our exponent here, we're going to be using this scenario that they give us, that the battery is charged to 35% after 50 minutes. So writing that in terms of our pronumerals given, we're going to give that the charge C is going to equal to 35, when T, our time after t minutes, is going to equal to 50. So substituting back into the equation that they give us, we get 35 is equal to 100 outside of 1 minus 2 to negative 50. Okay. Dividing both sides by 100 so I can get the bracket by itself, I'm going to get 0.35 is equal to 1 minus 2 to the negative 50k. Then I can get rid of this 1 here by minusing 1 from both sides. So 0.35 minus 1 is going to give me negative 0.65. And that's going to equal to negative k to negative 50k. I want to get rid of my negative here just because it's making it a little bit trickier than it needs to be. So dividing both sides by my negative 1, flipping those signs to a positive, I get 0.65 is equal to 2 to negative 50k. So because I'm trying to solve for k, which is in my exponent here, what I want to be doing is taking the ln of both sides to bring it down to the front. So I have ln 0.65 is going to equal to ln 2 to the power of negative 50k. I'm then going to be using my log laws. That's going to bring the exponent of a log or an ln function to the front. So I'm going to have ln 0.65 is going to equal to negative 50k times ln 2. To make negative 50k the subject, what I'm going to do is divide both sides by ln 2. So I get negative 50k is equal to ln 0.65 all over ln 2. The only thing that I need to get rid of to make k the subject now is this negative 50 in front of it, and I can divide both sides by negative 50 to get k by itself. So I get ln 0.65 all over ln 2 divided by negative 50. Plugging that one into your calculator and you get k is equal to 0.012429. And because this question is to show that question to 4 significant figures, I can leave my answer as 0.1243 as required. Okay, now that we've solved for the value of k in part A, we can then move on to part B. So part B, we had told that to prolong the service life of the battery, the charger may be set to switch off when the battery reaches 90%. So when the battery reaches 90% capacity, we know that the charge is going to equal to 90, so C is going to equal to 90 there. I now have for how long will the battery be on charge until it reaches 90% capacity. Now because this question says for how long, I'm now working for some sort of time, I'm solving for time here. So I want to solve for t, and like we wrote before, when C is going to equal to 90. So I can write that equation down. So I have C, my 90 value there, is going to equal to 100 outside of 1 minus 2 to the negative, we know my k value now, which I can write as 0.01243, and then my t value. So once again, we're solving for t, which is in my exponent. So I can do similar steps to how we did for part A. So starting off with, I'm going to divide both sides by the number sitting outside my bracket, so 100. 90 divided by 100 is going to give me 0.9 is equal to 1 minus 2 to the negative 0.01243t. I'm then going to get rid of my constant of 1 that's sitting outside my exponential. So minusing 1 from both sides, and I have 0.9 minus 1, which is going to give me negative 0.1 is equal to negative 2 to the negative 0.01243t. I then can get rid of my negative number again by dividing both sides by negative 1 like we did in part A. And I'm going to get 0.1 is equal to 2 to the power of negative 0.01243t. Now I've got my exponential in simplest form. I want to solve for t by taking the ln of both sides once again. So I'm going to get ln 0.1 is equal to ln 2 to the power of negative 0.01243t. Once again, using my log laws, I can take this power here and bring it out to the front of my ln 2. So I'm going to get ln 0.1 is equal to negative 0.01243t times ln 2. Dividing both sides by ln 2 now to get my t and my constant term out the front. So ln 0.1 over ln 2 is equal to negative 0.01243t. Once again, what I can do is I can divide both sides by my coefficient of my t value. So I get t is then going to equal to ln 0.1 over ln 2 divided by my negative 0.01243 value. And then if I plug that into my calculator, I therefore get that t is going to equal to 267.250, and writing that to 2 decimal places, I get 267.25 minutes, because that's what my t value was measured in. So that's how we answer part B, very similar to how we solve for part A, but we're just solving for t here when we're given a certain scenario. Okay, so moving on to the last part of this question here. So for part C, we have, by considering the first and second derivatives, describe the behavior of C for t is greater than or equal to 0 if the battery is left on charge indefinitely. So I've been given a hint here to work with the first and second derivatives to describe the behavior. So when we think about how the behavior can be described in terms of the first and second derivative, the first derivative tells us, is it going to be increasing or decreasing based on if the first derivative is positive or negative. And the second derivative tells us at the rate at which it's decreasing or increasing. Okay, so when we have a look at indefinitely, because we're looking at with a time value here when time is indefinite, we can imagine here, because we're working in t is greater than or equal to 0 as well, we're going to be looking at what's happening to the function as t gets bigger and bigger and bigger and approaches infinity in the positive direction. So infinite, think about infinity here. So we're going to be looking at where the function is approaching. Okay, so because we need to work with the first and second derivatives, we can write down ct as equaling to our function from before. So 100 outside of 100, outside of 1 minus 2 to the negative 0.01243t. Just expanding that out so that we can work with the derivative 100 times 100 to minus 0.01243t. So just expanding that out using my distributive law. So we know that my differentiation here, because I've got no t value in the first, I'm going to be really focusing on differentiating the second part of the equation because that's where I can see my c value. So to differentiate this, we're going to be using our rule in our formula sheet where we have a to the power of f of x, so deriving this one, is going to equal to a to the power of f of x again, times by the derivative of the exponent, so f of dash x, times ln a of the base. So here we're going to have that, but times by 100 because I have 100 sitting outside of my brackets. So what this is going to look like is my a value here is my 2, and my f of x is going to be my negative 0.01243t because that's where my variable that I'm trying to derive is sitting. So if I have a look here, dc on dt, so the derivative of c in terms of t, is going to give me negative 100 outside of 2 to the negative 0.01243t times by my derivative of the exponent, so just the number negative 0.01243t times ln a, so ln 2. Okay, if I have a look here, I have negative 100 and I can times it by my other constant term here that doesn't have a 2 in it, which is a negative 0.01243. So I then get a positive number. So I'm going to get 2.43 t times 2 to the negative 0.01243t times ln 2. So you can plug this into your calculator, just let t is equal to 1. But because t is always going to be greater than or equal to 0, if t is greater than or equal to 0 here, this function's always going to be 0 because we can't see a negative number out the front anymore because those cancelled out. So therefore we can say that dc on dt is always going to be greater than 0 for when t is greater than or equal to 0. So because we're talking about the behavior at the first derivative, we can say that the function is going to be increasing. Now we also want to use a second derivative to find the rate at which it's increasing. So is it going to be increasing at an increasing rate or increasing at a decreasing rate? So once again, we're going to use the same formula to find my second derivative. So I use my 2.43 ln 2 times 0.01243 times ln 2 again times 2 to the negative 0.01243t. So once again, I'm only interested in where my exponential was sitting. So I have my second derivative as this formula. I can simplify it a little bit now. So I have 2.43 times, this should be a negative 0.043 because that's my, once again, my derivative of my exponential. As you can see here, that's the power. So this would be a negative number. So once again, I can times 2.43 by my negative number and I get negative 0.030249. So just times in 2.43 by negative 0.01243 again. Then I have ln 2 and ln 2. So ln 2 times ln 2, like any other variable, we can just write that as ln 2 all squared. And then just times by my a of f of x. So my 2 to the power of negative 0.01243t, like that. Okay, once again, we're always going to be seeing when t is going to be greater than or equal to 0. And here we can see that this is going to produce a negative number because of the negative sitting at the front here. So therefore, we can say that my second derivative is actually going to be less than 0 when t is greater than or equal to 0. So therefore, it's going to be increasing at a decreasing rate. So what that looks like is, because we know that the second derivative deals with concavity, so let's draw my concave down curve just as a parabola here. When it's on the left-hand side here, it's actually increasing. Now, because it's concave down, it's still at a decreasing rate. What that means is that it's going to increase, but it's going to get flat. So you can imagine that this flat part here is your 100% of charge. It gets increasing, it's going to keep approaching to 100%, but because it flattens out, because it's increasing at a decreasing rate, it's never going to quite reach that 100% as you can see here. So it's almost as if an asymptote does exist here. So therefore we can say also never gets to 100%. So that's how you would describe the behavior of this exponential. So here we had a look at the first and second derivatives and also took into the effect as t approaches infinity, as t was greater than or equal to 0. So hopefully that helps to answer any rates of change questions that pop up. They're a little bit different based on every question that you get, so it's really important to have a look at what the question's asking us, what our variables are in our question, and whether we have to be using the derivatives or not.